Hi, I'm Ben Miller, and welcome to Life in the Fast Lanes. Data centers are essential to modern society. Networking speeds have increased dramatically over the past few decades, which has allowed data centers to transmit and process the high volume of data that the modern world uses to communicate and make complex decisions. Ethernet standards bodies have continuously developed faster data standards to keep up with the demand, as industry leaders reinvent and reintegrate new high bandwidth silicon, server components, interconnects, and systems into rapidly evolving, decentralized data center ecosystems. I talked to two of Keysight's foremost experts in Ethernet. John Calvin is the lead planner for Keysight's data center solutions, and Charles Seifert is the product manager for Keysight's network test solutions. The three of us talked about the market drivers causing the demand for increased networking speeds, what developers need to know about the upcoming 224G per lane speeds, and the biggest test challenges that developers are going to face in the physical layer, protocol layer as they approach creating 1.6T Ethernet networks. Without further ado, let's go ahead and meet our experts.
Hello, my name is Charles Seifert, and I'm the Senior Manager of Hardware Product Management for Keysight's high-speed Ethernet products.
Hey, good day, everyone. My name is John Calvin. I'm a planner with Keysight Technologies. I'm a principal planner for our high-speed data center solutions and the technology that we use to plan our instrumentation and our products directed towards high-speed data center support.
So guys, network bandwidth demand is up 30 to 40% every year. What kind of applications are driving that kind of demand?
Yeah, the drivers of high-speed Ethernet demand are largely driven out of use of the networking interfaces or networking demands for high-speed data center support. Whether you're streaming something from Netflix or you're basically doing a search engine operation where your engine is trying to complete your search for you and query before you finish typing it. These are all great examples of advanced data center capabilities and features that require extremely low latency, high-speed communication, as well as increasing attention on efficiency as an operating mode for high-speed data centers. The combination of all these needs from a consumer standpoint are helping to drive this rapid evolution here. We see a new data specification emerging every 3.5 to 4 years now.
We have new technologies in the user space. So, for example, 5G is creating what they call X-haul, which is front and backhaul network bandwidth increased demands. And that affects many different Ethernet speeds. And another big trend is large enterprise networks are transitioning to cloud services, which means our companies that are involved around the world in providing cloud services, which are some of the largest companies in the world, are increasing the number of data centers and how much traffic bandwidth they have to deal with on a per second basis, which is a staggering amount of information. And also we have the effect of the global digital economy. What process do we have today that's not electronically managed to process, generated, any which way that you look at any aspects of our life, it's increasingly digitized. And then of course the hot technology is artificial intelligence and machine learning, which starting in 2024 will add significant amounts of what they call workloads into the network, which will further drive the demand for more network overall bandwidth in the network equipment infrastructure.
So how are these market trends affecting different players in the data center ecosystem?
From an industry point of view, everything is affected, from silicon chip communications, silicon chip development, to intellectual property software firmware that runs on top of those chips, to the interconnect devices that takes and connects together our switches and routers and servers and all different types of networking interconnect equipment that goes into the data center equipment rack. All of that is called network infrastructure, basically. And that network infrastructure not only has to grow as far as the number of facilities around the world. For example, there are cloud service providers that have over 200 data centers connected around the world. Right, that's just one. And these data centers all have to talk to each other. And so as we connect all these data centers, everything to do with driving these connections, the connections have to be faster. So what we used to think was 100 gig E, oh my gosh, that was going to be the fastest speed ever. Well, today, 400 gig E is being the cloud companies are moving from 100 gig E to 200 gig E to 400 gig E. 800 gig E is in the near future, and 1.6 terabit is right behind that. So as all these new applications we discussed earlier converge onto these cloud data centers, as an example, the amount of equipment, the amount of the bandwidth, the throughput of the traffic that equipment has to produce increases exponentially. So the entire ecosystem is affected from a hardware point of view.
the tendency for cloud computing now to push a lot of its data centers closer to the edge of their infrastructure has been heightened recently by geopolitics, where a lot of countries are now sensitive to where their data goes. And to get around this, we're starting to see the proliferation of data centers through Europe, United States, Asia, India, with an effort to move from a centralized data center design to a distributed one closer to your clients. And one of the reasons you see such a large proliferation of data centers is for that reason alone.
So what are some key careabouts in the industry, other than speed increases, obviously, are driving some of the changes in the standard this time around?
There's a technical objective here with getting power consumption down to a level that's scalable for the next generation of architecture. Um, we're coming from a regime at 100 gigabits per second, where a lot of these SerDes and PHYs that make up the communication backbone of these data centers are operating in excess of 20 picojoules per bit. And there was a point in time 10 years ago where that was an incredibly low number. But the fact of the matter is that number has progressively gotten halved time and time again. And there's really a race to the bottom in terms of power consumption per bit. Right now, the specifications that are emerging and the specifications that Charles spoke of a moment ago to get to 1.6 terabit are all targeting sub 2 picojoules per bit.
And with the advent of super high performance, what they call GPUs and CPUs that are used in AI and ML applications and in high performance computing applications, scientific and other kinds of big data intensive applications, all of that is putting pressure on these data center locations. So our new standards for 1.6 terabit, all of that is in an effort to reduce power but increase traffic throughput in the same volumetric space. When we talk to, let's say, a cloud data center or a service provider, if they can save a quarter of a watt per network port, that is a major deal. That is a major deal. And just think of it like this. There are multiple companies in the world that have more than 2 million servers, which implies several 100,000 switches and tens of thousands of routers. You can imagine what a quarter of a watt per physical port just might be worth. And our new standards that we're developing for 1.6 terabit, 800 gig E, all of those are moving in a direction that's going to reduce power even further than we are today.
So, John, could you give us a bit of insight into the process for developing a new physical layer Ethernet standard?
We spent the last 4 years wrapping up the 100 gigabit per lane physical layer specifications that you'd find in IEEE standards like 802.3 CK and the OIF CEI 5.0 specification thing. That technology was officially put to rest in 2022, the end of 2022, and we're now have our sights set on the next set of objectives. So we see OIF CEI 224 gig project starts. We also see IEEE 802.3 DJ as two of the principal areas where people are focusing their talents and their time to figure out 200 gigabits per second. And when I say 200 gig, I say that term loosely. It's really 212 gigabits per second to 200 or 224 gigabits per second, depending on whether or not you're IEEE or OIF. But in general, let's call that 200 gigabits per second for now. The specifications for the speed are a pretty major undertaking in terms of complexity. And we've never seen such a short timeline for delivery as we have for some of these emerging specs in front of us now. We're targeting completion of 802.3 DJ by mid-2025. That's really only 2 years from now. We've been working on it for the last year and a half. That would mean that we've been doing this for about 3.5 years, which is a record short time for such a huge undertaking. The development lifecycle actually starts ahead of the standard. The early adopters and the early research that goes into PHY design, basically just trying to validate that the silicon can satisfy the power and the signaling objectives. You can achieve certain channel loss objectives. That's work that all takes place behind the scenes. And then once it starts to show promise, you see the beginnings of a standardization process. You see project authorizations get started in IEEE and or OIF, and people start to bring together the best minds in the industry to really collectively design how this next speed grade could be used in the next generation of Ethernet.
What measurement challenges do you see developers facing and struggling with today, and how can Keysight Solutions and experts like yourselves help to solve some of those?
There are some real challenges in the measurement technology, the measurement science that goes behind this. It's not trivial. What we see is a heavy reliance on being able to control equalizer technology, transmit equalization. There's a complex reference receiver at 802.3CK, the most complex we've done to date, that has to be tuned for certain measurement operations. And that tuning process is a process that is well established in simulation. If you bring it into the real world, there are some problems that people encounter, not the least of which is noise floors and noise performance of instruments. We do these measurements today at roughly 40 gigahertz Bessel-Thompson roll-offs, and we have instrumentation bandwidth numbers that can satisfy these measurements quite well. We're starting to see some creative use of noise management. We have to manage the noise in our instruments to hit input referred noise levels that the specifications are for the first time mandating now. So all these technologies and these technical challenges come together in test automation that we provide the end users. The 802.3CK full physical layer measurement portfolio can be obtained from Keysight. They can be done on any instrument by hand, but it requires an intimate knowledge of the base specification. And there's a lot of subtext in these specifications where it may not be black and white how to do a test. So we've been in the specification process long enough to know really the intent of the authors in some case behind some of these measurements. And we've implemented them in our test automation. So you do not have to become a standards expert in order to evaluate vertical eye closure on your SerDes. So that simplifies the task quite a bit for most of our users who need this kind of measurement support. Never in the past have we ever seen such a strong reliance on the need to characterize interoperability at the component level. So a transmitter has to be characterized standalone. The receiver in that architecture also has to be characterized on its own. We have a receiver test, fully configured impairments are fed into receiver to test its performance. And we also have infrastructure to test the interconnects, be it active optical cable or just plain copper. We have test tools for that as well. And that basically breaks the problem down into manageable pieces, and each one of these pieces has to be tested against a spec. Traditionally, what's been done in this business is you hook it all up and you count the bit errors coming through and you keep your fingers crossed and you see if it works. And if it does work, you throw a party. Those days are behind us at this point. And particularly with the reliance on all this interconnect going in to serve data centers are kind of a one and done proposition. You set it up once, it has to fulfill its role for 7 to 8 years, and then it's going to be shut down. You don't get a chance to go in there and tinker with it or fix it after you've installed it. So the reliance to have all this stuff work the first time and to pass these interoperability tests has never been higher than it is today.
What are the biggest changes coming to the next generation of the standard that you think developers might need a little bit of a heads up about?
We've seen things like the sophistication of the reference receiver progressively get more and more complex. It used to be you had a transmitter FFE, which is a feed-forward equalizer, and you had a receiver CTLE, which is a continuous time linear equalizer. And that represented the totality of your signal conditioning and your link equalization system. Nowadays, for CK, we see a transmit feed-forward equalizer, we see a CTLE, and a decision feedback equalizer, all working in tandem on the reference receiver portion of that link. And as we go to DFE, the final decisions on this are still ahead of us, fortunately, but they're looking at how to support 40 dB channels at 200 gigabits per second. And this is an exceptionally challenging undertaking. And they're resorting to the use of maximum likelihood sequence estimation tuning methods to basically establish what the proper coefficient should be for all the equalizers in the chain. So we're seeing the introduction of partial response-based equalizers combined with CTLEs and FFEs all working together. It used to be we would see maximum 5, 6 tap equalizers. Nowadays, people are, at least in simulation, talking about 80 tap equalizers. I've seen some studies that suggest 200 gig links require 80 tap FFEs to make it work. That's an extraordinary jump from where we've been here, where a 5-tap FFE was considered to be pretty advanced. Now we're talking about 80 tap FFEs. So this is kind of a quick overview of the progression and the sophistication that continues to develop here in the receiver technology to make these high speeds and these BER numbers a reality.
My discussion with John and Charles ran way too long for just one episode, so I decided to split them into two. So in next month's Life in the Fast Lanes, you'll be hearing a bit more about the network and protocol layer testing for Ethernet standards, and we'll also be jumping into forward error correction and how important that is for the IEEE and OIF standards in order to maintain a good level of communication. But keep an eye out for that next month. In the meantime, if you'd like to learn more about Keysight's Ethernet solutions, please visit www.keysight.com/find/fast-lanes. But until next time, I'll see you on the fast lanes.